So now we're going to do another example here where we're calculating the enthalpy changes during this reaction. So here we have a reaction between carbon monoxide and hydrogen gas to produce methanol. And so we first have to actually write out the Lewis structures for the reactants and the product. Okay. So here we see for carbon monoxide, we're going to have a carbon-oxygen triple bond. And then for hydrogen, it's going to have a single bond between each hydrogen atom. There are two molecules of H2, so that's important because it's not just one single hydrogen bond, hydrogen-hydrogen bond, but it's two single hydrogen-hydrogen bonds. And then we have methanol, and so we have, if you look at the bond types here, we have three carbon-hydrogen bonds. We have one carbon-oxygen bond, and we have one oxygen-hydrogen bond. Okay, so when you're doing these problems, I guess the hardest part, of course, is to write out the Lewis structure. And then the next thing students will mess up when they're trying to look at the number of and the type of bonds between the atoms. Okay, so here we have three carbon-hydrogen atoms, we have one carbon-oxygen atom, and we have one oxygen-hydrogen atom. So it's listed out there. So to find the enthalpy, it's the summation of the bond energy of the bonds broken minus the summation of the bonds formed, that bond energy. So here we need to look up the bond energy for a carbon-oxygen triple bond. So if we look that up here, carbon-oxygen triple bond, its bond energy is 1080 kilojoules per mole. Okay, so we input that value. 2 times hydrogen-hydrogen single bond, so we have to look that up. So hydrogen-hydrogen single bond is 436 kilojoules per mole. So we input in that. Times 2, because there's two molecules of H2, right, in the balanced equation here. All right, so we add those values together, okay, and then we have to add up all the bond values for our product for methanol. So we have 3 carbon-hydrogen bonds, and so if we look up those values for the carbon-hydrogen bond there, it is going to be 415 kilojoules per mole. So 3 times 415 plus we have a carbon-oxygen single bond. The carbon-oxygen single bond is 350 kilojoules per mole, so 350 plus oxygen-hydrogen. So oxygen-hydrogen bond is 464 kilojoules per mole, so 464 kilojoules. All right, so we're going to add up bonds broken, bonds formed. Take the difference there and we get a negative 107 kilojoules. Okay. And so it's an exothermic reaction. We can see that just from the mathematical values. We can compare the value to the value calculated based off the standard enthalpy formation data. Okay, and so that value is negative 90.5 kilojoules compared to 107 kilojoules, negative 107. So each method has different values. Okay, there's going to be a gap associated with it. Okay, and this occurs because the average bond length strengths are given, and so we know that, say for example, this carbon-hydrogen bond, once it's broken, may require more energy, actually when it's released, than it does for the others. So they're not all equivalent, and that has to do with what's around it, okay, and how much energy is required or released. And so so these values are just approximate values for the most part. Okay, the next topic we're going to talk about, I think that's the last, no, there's 2 more topics. Okay, the next topic we're going to talk about in this section is ionic bond strength and lattice energy. So we talked about bond energy for covalent bonds. Now we're going to talk about the energy that exists between ions in when they form an ionic bond, and that's referred to as lattice energy. Okay, so by definition, lattice energy of an ionic compound is defined as the energy required to separate 1 mole of a solid into its component gaseous ions. Okay, so here we have a solid here that is going to be broken apart into gaseous ions. Okay, the amount of energy it takes to do that is referred to as the lattice energy. Okay. So lattice energies are endothermic or positive values. Okay. And so we need to learn a little bit about comparing the different lattice energies for different ionic compounds. All right. So for sodium chloride, the lattice energy here is 769 kilojoules. So it requires 769 kilojoules to separate 1 mole of solid sodium chloride into gaseous sodium ions and chlorine ions. When 1 mole of each of gaseous sodium and chlorine ions forms a solid sodium chloride molecule, 769 kilojoules of heat is released. So the lattice energy of an ionic crystal can be expressed by the following equation. Okay, and so here it's derived by Coulomb's law. So the enthalpy of lattice, or the lattice energy basically, is equal to C, where C is a constant. It depends on the crystal structure of the substance. Z plus and Z minus are the charges on the ions. Okay, so Z plus would be the cation, Z minus would be the anion, R naught is the interionic distance. Okay, so that's the distance between the sum of the radii of the positive and the negative ions. So it's the distance between the two ions. The lattice energy of an ionic crystal increases rapidly as the charges of the ions increases and the sizes of the ions decrease. Okay, that's a very important statement there. I'm going to highlight it. The lattice energy of an ionic crystal increases rapidly as the charges of the ions increase and as the sizes of the ions decrease. All right, so for example, when all other parameters are constant, doubling the charge of both the cation and the anion triples the lattice energy. All right, so here's an example. We have lattice energy for lithium fluoride. The lithium has a +1 charge. Fluoride has a -1 charge. Okay, it's 1,023 kilojoules per mole. Whereas magnesium oxide, the cation and the anion both have a magnitude of 2. So magnesium is +2, oxygen is -2. It has a lattice energy of 3,900 kilojoules per mole. So you can see the large difference here. So, you know, they're both ionic compounds, but because they both have their cations differ by a factor of 2 and their anions differ by a factor of 2, their magnitude is going to differ by a factor of 4. Okay. So if we compare the sizes of these two guys, they're roughly about the same. So 200 picometers for both compounds. Okay. So here it's just a direct comparison of charge differences and how that matters. And the greater the charges on the ions, the greater the lattice energy value. Also, when you talk about distances between the atoms, that also affects the lattice energy. The smaller the distance, the greater the lattice energy strength. So for example, when we compare the lattice energy of magnesium fluoride, MgF2, to MgI2, so F2 is smaller than I2, fluorine is smaller than iodine. It's higher on the periodic table, it's smaller. So you can see the lattice energy differences here. For MgF2, it's higher than MgI2. And that's because of the smaller ionic size of F minus compared to I minus. Okay, so the smaller the size, the greater the lattice energy strength. Okay. So here we have an example. It says a precious gem ruby aluminum oxide contains traces of chromium 3+. The compound Al2Se3 is used in the fabrication of some semiconductor devices, which has the largest lattice energy, Al2O3 or Al2Se3. So we're really comparing oxygen versus selenium, right? O versus Se. So if you look on the periodic table, you can see that oxygen is higher up on the periodic table, so it's going to be smaller. Okay, so aluminum's +3 in both compounds. Oxygen's -2, selenium's -2. They're in the same group. But oxygen's higher on the periodic table, so that means its size is smaller. So the smaller the ion, remember your periodic table trends. You need ionization energy, you need to know that, you need to know atomic radius, and you need to know electronegativity or electron affinity, either one of those. You need to remember that from the last test, because it's applicable, of course, to these types of questions. You have to be able to compare two different elements and know that one's larger or smaller than the other. You have to know that. So that's what we're doing here. And so we know that oxygen is higher on the periodic table, so it's going to be smaller than selenium. Okay, it's in the same group, but oxygen's above selenium. So oxygen's smaller, and so that means that oxygen, the compound that has oxygen in it, would have a higher or larger lattice energy. All right, I think this is the last topic here, and there's no real examples here. This is just sort of like FYI. Information, the Born-Haber cycle. So here, with lattice energies, you can't directly measure the values. You can measure them indirectly. So sort of by using Hess's law. Okay, so here we have several different steps here. We're starting out with cesium and fluorine. Okay, as cesium as a solid, fluorine as a gas, F2. All right, and then we have the enthalpy of sublimation for the metal cesium. Okay, and it becomes a gas. Okay, and so there's a certain energy associated with it. Okay, starting from solid to a gas. So these are, both elements in their natural state. Fluorine's a diatomic molecule, cesium's a solid at room temperature. Okay, so the amount of energy it takes for cesium to go from a solid to a gas, there's a certain value there associated with it. Okay, and then for cesium to become a ion, okay, you have ionization energy of that metal that's required. Okay, so that also takes a certain amount of energy to remove an electron. All right, so cesium is now positively charged and it's a gas. Okay, and then you have to remove one fluorine atom from this molecule. It needs to become just fluorine by itself, and so it takes energy to do that. The bond associating energy of a nonmetal for fluorine is needed. Okay, and so then you get to a point where you have cesium that's a cation and then fluorine that's neutral. So you need to remove that electron, right? So you have energy, actually not to remove it, but actually to add an electron. So that would be an electron affinity value there to add an electron to fluorine. Okay, so now we have cesium that's positively charged, fluorine that's negatively charged, and then it's going to form cesium fluoride, an ionic compound. Okay, and that's going to have a certain lattice energy associated with it. So basically, that difference there, the value, is going to be your lattice energy. And so you can also use Hess's law to add up each individual energy. Okay, and then you end up with your lattice energy for your cesium fluoride. All right, The final section is about molecular structure and polarity. So we're going to talk about structures of small molecules using valence shell electron pair repulsion theory, or VSEPR theory. Explain the concepts of polar covalent bonds and molecular polarity, and access the polarity of a molecule based on its bonding and structure.